Can adiabatic quantum computing be made universal? Imagine a future where computers can solve complex problems by gently guiding quantum systems from simple states to intricate solutions. That's the promise of adiabatic quantum computing. But can this method do everything a regular quantum computer can? Let's find out. Adiabatic quantum computing is a way of doing quantum calculations by slowly changing the energy landscape of a quantum system. It starts with a simple setup where the system is in its lowest energy state, called the ground state. Then, by gradually changing the system's energy configuration, it ends up in a state that encodes the answer to a problem. This process relies on the adiabatic theorem, which says if you change things slowly enough, the system stays in its lowest energy state. Now, adiabatic quantum computing is not just a neat trick. It is considered a universal model of quantum computation. That means, in theory, it can perform any calculation that a standard quantum computer can do. Both models are polynomially equivalent, which is a fancy way of saying they can do the same tasks efficiently. So, if you have enough control over the system, adiabatic quantum computing can, in principle, run any quantum algorithm. However, turning this into reality is a different story. To make adiabatic quantum computing truly universal, you need to implement a wide variety of Hamiltonians. These are the mathematical descriptions of the energy of the system. For universal computation, you need Hamiltonians that include complex multi-qubit interactions and sometimes non-stoquastic terms, which are special kinds of interactions that can change signs and make the system more powerful. Most current hardware, like quantum annealers, are designed mainly for optimization problems. They don't support the full range of Hamiltonians needed for universal quantum computing. Researchers are exploring new hardware options, such as superconducting qubits or Rydberg atom systems, which could someday support the complex interactions required. These systems would need precise control over many qubits and their interactions, which is a big engineering challenge. Despite these hurdles, the theory remains clear. Adiabatic quantum computing can be made universal because it is equivalent to gate-based quantum computing. But building hardware that can do this reliably is still a work in progress. It's an exciting area of research, with many scientists working to develop the necessary technology. If successful, universal adiabatic quantum computers could revolutionize how we solve problems in chemistry, materials science, and beyond. So, in summary, yes, adiabatic quantum computing can be made universal in theory. But in practice, it requires advanced hardware capable of implementing a broad set of Hamiltonians with high precision. This remains a key focus in the emerging field of quantum technologies, promising a future where quantum computers can tackle any challenge we throw at them.